Okay, in 6.1 we start to talk about anti-differentiation. So I give you a little background and I say that you know how to take derivatives of functions. So now we're going to start working backwards and get the function from the derivative. And this process is indeed called anti-differentiation. So we'll call the derivative, so check this out, we'll call the derivative f of x, and the antiderivative is capital F of x. Alright, so that means, if I'm looking at this example, this derivative you would find behind the integral symbol. Okay, it's going to be a function of x, and I indicate that by saying dx. So I want you to notice that there are no endpoints, so there's nothing here and nothing here. So this kind of differentiation is one without the endpoints, and it's called indefinite differentiation, and we'll mention that again. So what we're saying is, if 3 was the derivative, what could have been the original function? And that original function could have been 3x plus any number, so we're going to say plus c. So if you take the derivative of 3x plus c, you will get back 3. So you always have this little answer key built in. So here are some other possible capital F of x functions you could have gotten. So you can see, because we have these constants here, here, here as possible candidates, you need to account for that, and we do that by the plus c. Okay, so we can say the antiderivative is capital F of x equals 3x plus c, and that allows for all possible answers. So don't forget the c. Okay, the next thing we're going to do is find derivatives or antiderivatives of a variable raised to a power. Alright, so here's this example. We have, let's see, example 2 is what we're talking about. So what if the integrand, which is the function behind the integral symbol, is x, and then we indicate we're taking the differential with respect, taking the antiderivative with respect to x by having the dx. This is your problem. You want to take the antiderivative. So remember, any x by itself is really raised to the first power. So here is our rule. To get the capital F of x, which is the original function back, you're going to write f of x equals, take your base, which is x, add 1 to the power, and if there's no power there, the power is 1. That gives us 2, and divide by the exact same thing. Then add the constant of integration. So let's try a few of these because I want to demonstrate why this is the generalized rule. So if our integrand was 7x to the third dx, what would our capital F of x be, or the original function, after we did the integration? Well, the 7 comes along for the ride. It is just the constant, just like it's the constant right here. Then you have your x, add 1 to that power, that gives me 4, divide by that same power. So whatever you have here is going down here as well. And don't forget the constant of integration. Alright, let's do one more. What if you had, we'll do a fraction. What if I had 1/2 times x to the 3/2, and then dx to indicate that x is the variable. So I'm going to write down the constant 1/2. I'm going to write down the x. Now I'm going to add 1 to 3/2. If you add 1 to 3/2, you want to add it as 2 over 2. That's going to give me 5 over 2 here. Now I'm going to divide by 5 over 2, but couldn't I really multiply by 2 over 5? So the 2 goes up here, the 5 goes here, because dividing by 5 over 2 is identical to multiplying by 2 over 5. So make sure you understand that. and then don't forget the constant of integration. Okay, so what's my final answer going to be? These 2's will cancel. I'm going to be left with, so I'm just going to put a little arrow, and I have x raised to the 5/2 over the 5 plus c. So that is your final answer. All right, so let's continue on the next page. So far we have gone through example 1. Oops, let me just fix that. Okay, example 1 here, when you have a constant behind the integral symbol, and example 2, when you have the variable raised to a power, and that power would be 1 in this situation. So we have our nice generalized formula, which we've gone over. Let's look at other rules of integration. So this will be integration when you have e, and I really should say e to the x, because that's the situation we have going. So look at what's behind the integral symbol. So your integrand is e to the kx. To take the anti-differentiation of that, you're going to say e to the kx. If I was taking the derivative, I would have said times k. Since I'm taking the antiderivative, I divide by k. So here is the general procedure. Here is the general procedure when you have a constant in front of the e to the x. So let's do one over here. So what if I had 12e to the 2x dx? My procedure is following this outline right here. Write down the 12. Write down your e to the 2x, because remember we write down what we see. Remember that you would have multiplied by 2 because that is the derivative of the exponent. But since we're doing anti-differentiation, instead of multiplying by 2, we're going to divide by 2. And then add your constant of integration. Okay, once you reduce this fraction, your final answer is going to be 6e to the 2x plus c. All right, I want to next talk about natural log, but I want to have some more space, so we'll do it on the next page. Okay, here is your information about natural log and how we handle that and how we recognize it. So I want to go over this by using the power rule and showing how the power rule can sometimes fall apart, and when it does, that's your tip-off, you have natural log. So, for example, what if I had 1 over x to the 7th dx, and I wanted you to take that integration? What you would first want to do, because we don't know how to undo the quotient rule, make this x to the negative 7 dx, and that's behind the integration symbol. And so to take that antiderivative, you would write down your base. You would add 1 to your power, which means making it less negative. So if you add 1, the power ends up being negative 6, and then I'm going to divide by negative 6 as well, plus the constant of integration. Now you certainly could clean this up, and it would be advisable. Why don't we have that be negative 1 over 6x to the 6th plus c. Okay, that's a better answer. So, no problem dealing with negatives. Now, let's do the natural log case. So I don't know its natural log yet. Here is the problem. I have 1 over x dx. Okay, so I don't know how to undo the quotient rule. I change my format so that I have x to the negative 1 dx. Alright, so I'm going to take the anti-differentiation. That, following the power rules, is going to be x, add 1, that's to the 0 power. No problem yet. It's when you try to divide by 0, which is undefined, so you can't do that. Game over. You have to recognize there is a problem. So this is the solution. When your integrand is x to the negative 1 when you bring it up to the numerator, that is your tip-off that your original function actually was natural log of x plus the constant of integration. So take the derivative of natural log of x, and remember you get 1 over x times the derivative of x, which is 1. So this indeed was the function that you get. So that's your natural log of x. So make a note of that. Memorize it. Know that if you are trying to do the power rule or trying to undo the power rule and you get a 0 in your denominator, that should be your trigger to go back and look at it again and recognize that the original f of x function was a natural log. Okay, let's move on to the next page. Alright, so you can see where I left off up here with natural log. So now this is important to know. Just like when we took derivatives, you can move from left to right and take a derivative of each term when the terms are connected by addition or subtraction. Same thing is true with integration. So the integral of a sum or of a difference is the sum of the integrals or the difference of the integrals. Okay, so we have some practice problems now, and these are all based on what we've learned so far. So let's do them. I would pause the video now, go ahead and do those if you don't have them filled in already from class notes, and then you can check what I've done. Okay, so hopefully you've done some work now. So I'm looking for the f of x, the capital F of x, and this is my original function behind the integrand, which I understand was the derivative. So it's a constant, so my answer is going to be 7x plus c. Again, take the derivative of that, you should get the integrand back. Here is the power rule. So doing the power rule, I write down the x, I add 1 to the power, that makes it 3, and I divide by the same number, plus c. Okay, here comes e to the 2x, so I'm going to write what I see, which is going to be e to the 2x, and then remembering that I'm doing anti-differentiation, I would have multiplied by 2 if I was doing derivatives, but I'm instead dividing by 2, and then add the constant of integration. Okay, so far so good. Okay, here we've changed our variable. Our variable is now t. So I'm now looking for f of t, not f of x. So f of t equals, I see I have a power rule in play, so I'm going to write down the t. I'm going to add 1 to the 7 halves, that becomes 9 halves. I would divide by 9 halves, but the other option, which is even better, is multiplying by 2/9. So that's what I'm doing, and then add the constant of integration. Okay, here's another power rule. We're back to f of x. So that's going to be x squared over 2 plus c. Okay, this last one has 3 terms, so that's not going to throw me off. I'm just going to look and see whether it conforms to what I know, and I see that the second term, 3 over x cubed, really needs to be written as 3 times x to the negative 3. Then I see I have an x in the denominator of the last term. That is my tip-off, is going to be natural log. Do not waste your time bringing that up. So let me just write over this one little thing. So why don't we I'm going to move this x3 up here as x to the negative 3. And then I'll do this in pink so you can distinguish it from the other problems. So here I'm looking for f of x. My first one, just power rule. So that's going to equal x to the, add 1, 4. Now you're going to bring the 4 down, but there's already a 3 there. So 4 times the 3 makes that a 12. Plus, okay, so I have the 3. This is going to be x to the negative 3, add 1, that makes it negative 2, and then divide by 2. And what I can do is put the 2 down here and make this a positive 2 in the denominator. And then the last piece is just 3 natural log of x, and I'm going to add the constant of integration. So those are good 6 solid problems that you want to be able to work through and understand. So if you need to, go back and listen to that again. Okay, this page gives you a little summary of what we have done so far. So remember that anti-differentiation can also be called integration. Anti-differentiation of an indefinite integral, no endpoints, gives us the original function plus c, the constant of integration. Anti-differentiation of a definite integral will give us a number. Okay, so we haven't done that yet. We have estimated it using Riemann sums, and we'll get to doing definite integrals when we get to 6.3. Okay, that's done. Okay, be on the lookout for 1 over x. Remember, that's going to be natural log. And don't forget to always include the constant of integration. Okay, there's one more thing we want to go over, and that is the chain rule. And so to give me some more room, I'm going to do it on the next slide. All right, so example 1 right here is going to be the chain rule. So let me do this out down here. So the chain rule is going to be undone. So I'm going to write down the exact problem that we had here, and I'm going to explain why I get what I get. And then we're going to talk about the k. So here's the chain rule problem. So what I'm going to do is I see I have a power rule going. So my f of x will equal exactly what I have there in parens, 1 minus 2x. Okay, add 1 to the power, that makes it 4, divided by 4. Now, because this is not just plain old x, I have to think about the chain rule. I would have multiplied, if I was taking the derivative, by negative 2. Instead, I'm going to divide by negative 2. So down here, I'm going to put a negative, and I'm going to say times 2. And then don't forget the constant of integration. Okay, so my f of x is going to be negative. I can put the negative up top. You can leave it in the bottom, but you're usually going to see it up top, so I always bring it up top. And then this is going to be 4 times 2, which is 8, plus c. So that is your chain rule. Okay, now let's talk about the c part, or the k part. So what they've done in these problems, they have given you most of the answer, and they want to figure out what's missing. So let's compare. My answer down below, I have a c, they have a c. I have the exact same thing here. I have 1 minus 2x to the 4th. So we have this just as it stands. What's missing? What's missing is, this is kind of a 1 hiding here, right? What's missing, and I'll change the color so we can see it better. This is what's missing. So in this problem scenario, k is going to equal negative 1/8. All right? So I want to do the next one, so I'm going to erase this slide, so make sure you understand what I have done here. Okay, so now I'm going to pull up that slide again. Okay, so continuing, let's look at this problem. Do you see how there's a k here, and they've taken the integration for us? So my approach is to come over here, write down what was behind your integral system, that your integral symbol, that was your integrand, and go ahead and solve it. I see it's an e problem. I'm going to write down the 3, the e, and the x over 10, because I know I write down what I see. I would have multiplied by 1 over 10, because that's the derivative of the exponent. Instead, I'm going to divide by 1 over 10. Dividing by 1 over 10 is just like multiplying by 10. So I'm going to multiply this by 10, and then don't forget about adding your constant of integration. Okay, so let's clean this up. The 3 and the 10, I can combine my multiplication. So that's 30e to the x over 10 plus c. All right, so Now we're going to compare what they have and what we have. Okay, we both have C's. We both have e to the x over 10. What's missing is the k. So in this situation, the k equals 30. So you should be able to do that. I want you to practice it. It will be assessed in this exact format. Let's move on to the next page. So we have some more, what I'm going to call k problems here. So let's do number 3. So I'm writing out what's behind my integral symbol. That's your integrand. It's already set up so that I can solve it because it's raised to the -2, so that helps me not have to deal with a quotient. So when I solve that, I'm going to get, write down what's in parens, 5x minus 7, add 1 to the exponent, that's going to make it less negative, so it's going to be -1, divide by -1, recognize you have a chain rule situation, you would have multiplied by 5, instead divide by 5, so that means 5 is going to join, it's going to join the -1 in the denominator, and then add the constant of integration. Okay, so let's clean that up. So I'm going to put a negative out front, and I'm going to, because I'm looking at this answer, I'm going to leave that the way I found it. So that's a negative there. I have a 5x minus 7 to the -1 all over the 5, remember the 5 from the denominator, plus c. Alright, so now we're going to compare. We both have the c's, we both have 5x to the -7. What does k equal? K must be -1/5. So in this situation, k equals -1/5. Alright, I'm going to erase this and we're going to go to the next number 4. Okay, let's look at number 4, and we'll do 4 down here. So what I'm going to do is, the first thing I'm going to do is conform this so that I can use my power rule. So I'm going to bring up the 8 minus x to the -4ths now, and then I have the dx. Okay, let's go ahead and find f of x, capital F of x. So I'm going to say f of x equals, 7 comes along, 8 minus x, -4 becomes less negative by 1, that makes it -3. That -3 also goes in the denominator, and then what I'm going to do is look at the chain rule inside. If I was taking the derivative, I would have multiplied by -1 because of the negative x. So instead, I'm going to divide by -1, which means that -1 is going to just join the -3 down in the denominator. And then I add my constant of integration. Okay, cleaning this up and looking at what they have for the answer, I'm going to bring the 8 minus x to the -3 down. -3 times a -1 will be positive, so I'm going to have 7 here, +3 down below, and then next to the +3, I'm going to have 8 minus x. When I bring it down, it goes to the +3 power, and then add the c. So now look what I have. The denominator matches up except for the 3, and the k has to be 7/3 because that's what's missing. So in this situation for number 4, k equals 7/3. Alright, so you've had 3 practices on this, or 4 practices on this, so you should be able to do the k problems and have a strategy for attacking them. Moving on to the next page. So this last problem is a very important problem. Not that the other stuff wasn't, but this is a problem that allows us to eliminate the c by virtue of additional information in a problem. So you want to be able to do these, so listen to this carefully. So let's read this problem together. It's on position, okay, so it says a ball is thrown upward from a height of 256 feet above the ground with an initial velocity of 96 feet per second. All right, so I'm going to sketch the position function. It's thrown up in the air, and then it's going to hit the ground. So this is going to be the position, or the height, and this is going to be the time it takes to reach that. By virtue of the problem that I've read so far, I know that this point right here, the purple dot, is 256 feet. So that's 256 feet. What else do I know? I know that the velocity initially, so that's at 0, height, is going to be 96 feet per second. I also know the position initially at time 0 is 256. Okay, so I know those two things. From physics, it is known that the velocity at time t is vt equals 96 minus 32 feet per second. They want me to find the position function, which is st. So what you have to recognize is that vt is the integrand. So put this behind the integral symbol. Okay, my variable is t, so I'm going to say dt and not dx. All right, to find the original function, that's your capital F of t, but we're going to call that s of t because we know exactly what it is. You're going to just integrate. So I'm going to get 96 as a constant, so that's going to be 96t, because I'm going to add the variable, minus power rule, 32 t squared over 2 plus c. So let's write that out down here. Because I know it's the position function, I'm going to identify it as st. So st is going to equal 96t minus 32 divided by 2 is 16, minus 16 t squared plus c. Now, because you have information about the initial height, you can do the following. You can say, let's see if we can figure out what c is. At time 0, plug in zeros. Here's 0 for t, minus 16, this is 0 squared, plus c. I know the position at time 0 has to be 256. This is 0, this is 0. That makes c equals to 256. Okay, so that's an important feature. So what I'm going to do is I'm going to write this function here. So this is s of t, and that s of t is going to be 96t minus 16t squared plus, not c, but plus 256. Okay? So now I'm going to erase what I have written so that we can continue to add to answer B and C below. Alright, so now tackling part B. How long will the ball take to reach the ground? So they want to know, when does the ball go right there to that t? So you have to recognize that they're just asking you for the 0 of the function. So you're going to take your position function, and I'm going to factor out a negative 16, so I make my problem a little bit easier to factor. So take a negative 16. Now let me go back for a sec. Guess I'll set that up better. Okay, so I have s of t equals negative 16. Okay, I want to have the t squared in front, so that's going to be t squared minus 6t minus 16. Set that equal to 0. That means you're going to have to factor what's in parens. So when I factor, I get the following. I'm going to get t minus 8 and t plus 2. So therefore t is going to equal 8, and t will equal -2. This does not really make sense, so 8 seconds is my answer. It'll hit the ground in 8 seconds. Okay, the next thing they want to know is how high will the ball go? So you have some options here. You want to look at this figure and realize, oh wait, this top right here has a slope of 0. The slope function is your VT. So to answer C, you're going to first figure out, so this is 8 seconds here, you're going to first figure out what time it reaches that height. So let's figure out how we're going to do that. That time is where the slope is 0. The slope function is your VT. So where does VT equal 0? Okay, I'm going to pause for a second and erase what I have here, and then we'll resume. Okay, so now I have some space. So I want to know, when is VT equal to 0? So my VT function is 96 minus 32t. So when does that equal 0? And that equals 0 where t is 3 seconds. So right here is 3 seconds. That does not answer the question, however. So what I want to do is figure out what is the height when t is 3 seconds. So you need to go back to your original position function with the constant of integration removed, and you're going to evaluate s of 3, so 96 times 3 minus 16 times 3 squared plus 256. And I believe you're going to get 400 for that. So I'm just going to check that, and it'll be 400 feet on my units. So let's just check that. Yep, I went to my fancy calculator, and I figured out that that position at the highest part of its arc will be 400 feet. So this completes the 6.1 lesson. Go back over and listen to it again, or listen to the parts that you have problems with.